Good day everyone and welcome to our presentation on digital stethoscope. Before we dive into the details of the project, let me give you a brief overview of the presentation. We will begin with the motivation behind the project and why a digital stethoscope is required. Next, we will discuss the literature survey, the implementation structure, the block diagram of the hardware. We will then move on to the preamplifier and the filter blocks and the circuit designs. We will also discuss the challenges that we faced during the implementation and the proposed improvements. Finally, we will conclude with the demonstration of the final amplified and filter hardware sound waveform. So motivation for the project. Before we jump into the technical details of the project, let me first explain the motivation behind it. The stethoscope is one of the most widely used medical instrument and it has been in the use for more than hundreds of years. However, traditional stethoscopes have certain limitations. For example, they may not be able to pick up faint heart sounds or the sounds may be too difficult to interpret. It is difficult to amplify and filter the sound that are heard through the stethoscope. Also, it is challenging to record and store the sound for future analysis. In addition, traditional stethoscope requires a skilled practitioner to use them properly, as heart diseases are the leading cause of death worldwide. Identifying the cardiac dysfunction requires important clinical experience and concentrated listening skills. So, um, to overcome these limitations, we need a new kind of stethoscope, a digital stethoscope. Literature survey. To design and implement this project, we referred to various published papers on topics digital stethoscope. These papers helped us to structure the project and come up with a block diagram for the hardware implementation. Preamplifier and filter block. So in our hardware implementation, we have used a preamplifier and a filter block. The preamplifier is a BJT based differential amplifier and the filter is a fourth order Bessel bandpass filter with a frequency range of 20 to 600 Hz. These blocks are essential for amplifying and filtering the heart sound. Circuit design of the preamplifier. Now let's take a closer look at the preamplifier circuit design. We have used a BJT based differential amplifier and a current mirror for the constant current source. We use a negative 12 volt of supply for the current mirror. This ensures a constant current flow through the differential circuit. So our input voltage through our mic will be in the range of around 15 to 20, 30 millivolts and we are looking for a gain of around 100x. Circuit design of the fourth order Bessel bandpass filter. So now let's move on to the filter. The desired range for the filter, as I said, was 20 to 600 Hz, which is frequency range of human heart sounds. The Bessel filter was chosen for its linear phase response, which helped preserve the integrity of the signal. Block diagram. Here's a block diagram that shows the different blocks in the hardware implementation. Stethoscope head block, the mic circuit block to take the input of the heart sound, then signal conditional block which includes our preamplifier to get the gain of around 100 Hz, then the filtering block to remove the unwanted and desired noise signals, and finally the output on this stethoscope that oscilloscope that we'll be plotting. So differential amplifiers design. So as I said, we have used a BJT based differential amplifier. It is an essential component of our project block. It amplifies the difference between two input voltages, and we used various current and voltage expressions for differential amplifier design, which we refer to the published papers as I mentioned in the literature survey slide. We've also conducted a small signal analysis with a differential amplifier. This analysis helps us to determine the gain and the frequency response of the amplifier, and the calculations are given in the slide as follows. Okay, so the picture of the differential amplifier circuit. So this here shows the hardware implementation of our BJT based differential amplifier, and this is our simulation circuit. And from here we can see the plot and the gain. So for amplitude given amplitude of around 50 3 millivolt, we are getting around 6.3, which is a gain of more than 100x. So we are successfully able to implement and achieve a gain of 100x using our BJT based differential amplifier. CMRR analysis. We have also performed the CMRR analysis of differential amplifier. CMRR stands for common mode rejection ratio, and it helps us to understand how well the amplifier rejects common mode noise. We have used the various expression for calculation of the CMRR. Filter design. So now let's take a look at the gain versus frequency curve of the different types of filters, namely Bessel filter, Butterworth filter, Chebyshev, and elliptic filters. Among these, we chose the Bessel filter for our project because it has a flat gain response and linear phase response and a good time domain characteristics. We did not want any ripples in our filtering stage, so that's why we chose Bessel filter, as we can see its response from this plot. So high pass filter. Now moving on, let's take a look at the high pass filter block. We implemented a second order high pass filter to remove any unwanted low frequency noise from the signal. The frequency response analysis of the filter was done using an oscilloscope, and we achieved the desired threshold of around 20 hertz, 25 hertz. And this here shows our this part shows our implementation of the high pass filter. Similarly, here we have some pictures showing the low pass filter circuit implemented on the breadboard in our lab. We can also see the output plot photo showing the frequency response analysis generated using the oscilloscope. The filter has a cutoff frequency of around 600 Hz. After implementing both the high pass and low pass filter, we combined them to create a fourth order band pass filter. This combined filter was able to filter out any unwanted noise in the signal and provide us with a clear and a clean heart sound waveform. So this here shows our high pass filter, this here shows our low pass filter, and we have combined them, cascaded them to get our desired frequency range. In this slide, we will be discussing the input and output impedance values and the plots. The input impedance refers to the impedance of the amplifier seen from the input terminals, while the output impedance refers to the impedance of the amplifier seen from the output terminals. So, as we after our calculations, we found out that our input impedance to be 12.1 kilo ohm, while the output impedance is 28 milliohms, and we can see that in this plots also. Total harmonic distortion. The total harmonic distortion, or THD, is another important parameter that indicates the quality of the output waveform. It is the measure of the deviation of voltage of current waveform from ideal sinusoidal shape. THD quantifies the unwanted harmonics that are present in the voltage or current waveform using Fourier analysis. THD analysis is crucial for maintaining and enhancing power system stability. We calculated the THD value for our circuit and also plotted its frequency response using the oscilloscope. And here is our simulation plot, and these are the values. Now let's take a look at the final implemented hardware circuit. We used a breadboard to implement the circuit, and all the required components were connected according to the circuit diagram, block diagram, as we saw earlier. As you can see, this here consists of the BJT based differential amplifier. This block here shows our high pass filter, and this entire breadboard circuit shows our low pass filter, and we have cascaded it. And here bottom two images, we can show the frequency response analysis of our filter. When we gave the input to the differential amplifier, and we are taking output from the other end of this low pass filter, and then we have calculated this frequency response analysis, and we can see that our uh, lower threshold is 22.9, which is near about 20 hertz, and the higher threshold, upper threshold, is around 602 hertz, which is around 600 hertz. So we were successfully able to implement the filter as we desired, and our frequency range is around 20 to 600 hertz, which is enough to detect the heart sound waveform. So challenges faced during the implementation of this project, we faced various challenges like low quality microphone to capture the very faint heart sound, and noise from the power supply is inevitable. Filtering that is also a major issue, and the external noise from the surrounding is also uh, an issue to solve. Apart from that, since we have to use only the analog circuitry and we were not allowed, we have not used any microcontroller. So finding a proper research paper related to analog domain only can be challenging, as the filtering stage in most of the papers uses the software of the filtering process using the microcontroller and all. And managing the circuit complexity is also crucial, as fourth order Bessel bandpass filter is complex circuit and can be challenging to design. Now, taking input from the stethoscope without cutting, as suggested earlier, was challenging because we have to insert our microphone inside a tube of the stethoscope, and since we were not allowed to cut the stethoscope, and taking the input then from the other end of the stethoscope becomes challenging at, and as it intakes various surrounding noises also. So, and also the due to unavailability of the more sensitive microphone, we had to work with the existing microphone in the lab. Despite the success of our project, we did face some constraints while making it. For instance, we had limited access to some of the required components like stethoscope and a high quality mic, so which made it difficult to obtain accurate results. In order to further improve the performance for our digital stethoscope, we proposed a better quality microphone and implement noise cancellation, and we can use AI ML models to train our train that with our data uh, to get a better results, and use and with further improvement, what we can do is we can use surface mount components to make the circuit more compact and portable. So final heart sound waveform. So finally, let's take a look at the final amplified and filtered heart sound waveform on the oscilloscope screen. We were able to clearly identify the S1 and S2 heart sound waveform, which indicates the successful implementation of our digital stethoscope. So as you can see in this is our stethoscope block, and this here shows our mic, which is taking the input from this earpiece of the stethoscope. Now this here goes to the BJT based differential amplifier preamp, which is giving a gain of more than 100 plus, as we saw in the previous slides. Then this goes via this green wire. This goes to the uh, high pass filter, and from high pass filter it is here going to the low pass filter, and from low pass filter this wire hour shows the output, which is this probe is connected to the oscilloscope. So all of the red wires here shows the DC power source of 12 volt. The black one is showing ground. The blue one are showing negative 12 volt supply, and the green wire shows the inter circuit connections. So this the diff amp is connected to high pass. This high pass is connected to low pass, and then from here we are giving the output to the waveform. And this here is our S1 hard sound waveform. This here is S2. So in conclusion, what I say, our project aimed to implement the digital stethoscope using analog circuitry. We have successfully implemented a preamplifier, a filter block, and they combined them to create a fourth order bandpass filter. We were able to overcome the challenges we faced and propose improvement to further implement the performance of our digital stethoscope. And thank you for your attention.